Chicago. He's going to talk about Taut, sutured handlebodies as twisted homology products.
All right. Well, thank you, Nathan, for the invitation. It's a pleasure to be here. So I'm talking about Taut sutured handlebodies as twisted homology products. Before I get into what any of those words mean, I just want to give a bit of motivation. So I'm interested in studying three manifolds, and if I want to understand a three manifold, a sort of natural way to do this is to study the embedded surfaces within the three manifolds. And there are a couple of reasons for this. For one thing, we understand surfaces much better than three manifolds. And we can also use surfaces as a way to decompose our three manifold, cutting along them, to get sort of simpler three manifolds that maybe we can understand better and maybe use the information of the simpler pieces to glue back together and get some better information about the entire three manifold itself. So a few examples of this. If you are familiar with the prime decomposition of a three manifold, basically you're finding three balls to cut open along, or three spheres to cut your three manifold open along. Another example is the JSJ decomposition, which you're finding tori to cut along. And famously, if you choose the right tori to cut along, you get nice pieces, which are either Seifert fibered pieces or all hyperbolic. And then two other examples, Hawken decompositions are cutting along sort of more complicated surfaces. And this gives sort of an inductive structure to argue about your Hawken manifold. And then lastly, when it comes to sutured manifolds, if you have a taut sutured manifold, you have a taut sutured hierarchy or decomposition, which again gives way to inductive arguments about your sutured manifold. So in all of these questions, in all of these techniques, there's sort of the question of how do I pick what surface to cut along? How do I know what's a good choice for my surface? This is question one. How to pick a good surface. And as an answer to this, we want some notion of complexity of our surfaces, and some notion of probably a minimal complexity will tell us that that's a good choice. And so this sort of leads to question two. If we have some notion of complexity, how do we know a given surface is good? If you hand me just some surface out of nowhere and say, here's my notion of complexity, can I tell that it's sort of minimizing that complexity? And so I will get into in this setting what I mean by complexity and how we address the second question. In this setting, we're going to be considering a notion of complexity that is called the Thurston norm, which I'll get into defining a little bit later. And as a rough idea, before I even define what sutured handlebodies are, the sort of technique we'll use for knowing when a surface in a three manifold is sort of minimizing this complexity is by cutting open along it and asking if the three manifold with boundary that we get, which will be this sutured manifold, is this notion called taut. So let me get into defining a sutured manifold. So a sutured manifold, three manifold, is, well, we have the three manifold itself, and this is going to be a three manifold with boundary. And we're going to have this extra structure on its boundary that comes in the form of r plus, r minus, and gamma, where, well, r plus and r minus are subsurfaces of the boundary, where we're decomposing the boundary along this suture set, gamma, this collection of simple closed curves, embedded in the boundary. And when we cut along this collection of simple closed curves, this will split. We want to choose these so that it'll split the boundary into two pieces. And if we choose an appropriate orientation on our suture set, this will induce this orientation saying this one is r plus and this other one is r minus. So as a basic example of this, if we take a knot complement in S3, and we take S to be any Seifert surface for K, we can, as I was saying, cut open along this Seifert surface. So take S3 minus, well, maybe some open neighborhood of the Seifert surface, and define this to be our sutured manifold M. And then r plus and r minus will both be copies of S. And our suture set will just be the knot that we started with. And you can similarly do this with any Seifert surface associated to a link in S3. So this is the picture you should have. Well, this is maybe the example of what you should be thinking of when you're thinking, how do I come up with a sutured manifold? If you want an actual picture in your head, I'm generally looking at handlebodies. You can just think of, well, this is going to be a very boring one, something like this, where you have an oriented curve and you have r plus on this side and r minus on this side. So next, let's define the Thurston norm, our notion of complexity for our surfaces in the case of a knot complement or Seifert surface. So our notion of complexity is the Thurston norm, which is a generalization of the knot genus, if we're looking at a knot. So what is the Thurston norm? Well, let's first, this is, I guess, a quasi-norm on the second relative homology of our three manifolds with real coefficients. And we define this by first defining for any surface embedded in our three manifold, we can define the negative Euler characteristic, or chi minus, of our surface, which is roughly the negative Euler characteristic, namely the maximum of 0 and negative the Euler characteristic. So this is saying we ignore any sphere, disk, torus components. So this is if S is connected. And if S is not connected, we take, well, the sum over all components. And then if we want, so this tells us a notion of complexity associated to any embedded surface in our three manifold. And if we want to define the Thurston norm, we want to define this on a homology class. So for some homology class, we define the Thurston norm of this to be, well, let's look at the minimum complexity, the minimum of our negative Euler characteristic over any representative. Of our homology class. And well, this works for any integral homology class. We can extend it linearly to any rational and unreal homology class. And this turns out to be a really useful notion of complexity, as you might guess from the fact that it has Thurston's name attached to it. So just a few properties of this, which I'm not going to particularly use, but they sort of maybe illustrate why this is something intrinsically interesting. So properties of our Thurston norm. So if we look at this as a norm and we look at what the unit ball of this is, the unit ball turns out to always be a convex rational polyhedron. And this unit ball has this feature that's called fibered faces, which is to say, if we look at our unit ball, I'll just sketch an example of what this might look like. So this is just some convex rational polyhedron. And if we look at say we have a homology class, which we know is fibered in the sense that M fibers over, well, a representative of phi. If we look at the face, the top dimensional face that this lies over, and we look at any other homology class which similarly lies over this face, we know that psi has to fiber as well. So this is pretty remarkable. We tend to like fibered classes because this tells us that, this surface within our three manifold really tells us almost all of the information we want to know about the three manifold itself. We just need the extra information of sort of the monodromy as we glue this back together. And this tells us that if we have one fibered class, homology class, we can find a lot more very easily. All right, so let's move back to more of the words in my title. So a taut sutured manifold. Let me define that. So our sutured manifold is taut. If the three manifold itself is irreducible, which is to say any sphere in M actually bounds a ball in M. So this is our condition on M. And then we want our boundary subsurfaces R plus and minus. We want these to be incompressible. So any loop in R plus or minus, which bounds a disk in M, actually bounds a disk in that subsurface itself. So we want it to be incompressible and related to our notion of complexity, Thurston norm minimizing. On the first two conditions, that our manifold is irreducible and that R plus and minus are both incompressible, well, irreducible will, in the case of handlebodies, this will just always be the case. And R plus and minus being incompressible is more or less encapsulated by being Thurston norm minimizing. So if we're looking at a surface in our 3 manifold and we want to know, is this Thurston norm minimizing, the idea is we can cut along it, as we did with our Seifert surface, and ask, is the sutured 3 manifold that we get from this, is this taut? And maybe I'll remark that as I've defined this sort of perhaps seems a little bit gratuitous. I'm basically just reformulating what I was asking before, is this Thurston norm minimizing? But these extra conditions, this idea of tautness is related to the theory of taut foliations. And you can define tautness in that context in terms of admitting a foliation of a certain type. And that turns out to be the same definition as here. So this leads to our main question. How can we certify that a given presumably taut sutured manifold is in fact taut? And so to start off here, I just want to make an observation. That observation is, let's say that we have sort of the simplest example of a sutured manifold. Namely, our manifold M is, well, roughly one of our subsurfaces across an interval. And given my definition, I want so here my suture set should be roughly the boundary of R plus cross the interval. That's a set of annuli, not curves, but I can just collapse those annuli just down to curves. So this is if M is a product manifold. And in this case, well, M should always be taut. R plus should always be Thurston norm minimizing, just because this is, well, has a deformation retract, is homotopy equivalent to just our boundary subsurface itself. And so M should always be taut. And this case corresponds to, this is equivalent to if we're looking at a knot complement saying that our Seifert surface is, well, K is a fibered knot and S is a fibered class for the knot. But this is pretty restrictive. So this is a case where we know that we're taut, but it's, in general, we're not going to be encountering product manifolds. However, the observation I want to make here is that when we're looking at our definition of tautness, when we look at what it means to be Thurston Arm minimizing, this isn't really asking about sort of the nature of our manifold on the nose. It's asking about the homology of our manifold. And so this sort of leads the naive idea that maybe we don't want our manifold to be a product on the nose, but maybe if we just know that from a homological point of view, it looks like a product. That should be enough for tautness. And in fact, it is. So this is a fact which I'll attribute to Friedel and Kim, which is that well, what does it mean to homologically look like a product? If we look at the map induced on homology by the inclusion of R plus and R minus into our sutured manifold M, if we look at this map, this should be an isomorphism. So if this is an isomorphism, this is saying that homologically our three-manifold looks like a product. And so our sutured manifold should be taut. In this case, we say that M is a, well, rational homology product. So this gives us a bit more leverage if we want to try and identify something as being taut. We can just compute these homology groups and check what this map is and see if it's an isomorphism. And this hopefully gets us a little bit further than just looking for something that's a product on the nose. A sutured manifold. Let's say that, well, my M is a handlebody, a genus 2 handlebody. And moreover, let's assume that our suture set is just a single curve. So this means that our boundary subsurfaces, R plus and minus, will both be once punctured tori. So in this case, if M is taut, then in fact it's always a rational homology product. So in this case, we always get this isomorphism on homology. And the idea behind this is a little bit delicate. If we don't have, if we don't have this isomorphism, we can see that this says something about what this suture has to be. And I can show that, in fact, this suture has to be trivial in pi1 of the handle body, which will tell you that you're not taut. You're not pi1 injective. So the idea here maybe is there's just not enough space in this picture for anything to go wrong. If you're not a rational homology product, you're just, your gamma is sort of not doing anything interesting. And in contrast to this, if we make things even the slightest bit more complicated, well, our notion of just hoping for things to be rational homology products suddenly fails, suddenly doesn't capture the information we would hope it would. So if we look at now a genus 2 handlebody, but instead of a single suture, we'll take, well, we can't have 2 sutures. We need these curves to be separating. But we can look at a set of 3 sutures which separate the boundary into 2 pairs of pants. So I'll take this and hopefully figure out where I okay. So here I'm drawing the sutured structure on this genus 2 handlebody. And in this example, this turns out to be taut. You can see this if you're familiar with sutured manifold decompositions. You can do this is something that preserves tautness, and you can decompose along, for instance, this disk here. And that will give you something that's just a product on the nose. So this is an example of something which is taut. However, if you look at the pink curve, the pink curve is trivial in rational homology of the handlebody. But not in the in the boundary subsurfaces. So this gives an example. So M here is taut, but not a rational homology product. So rational homology isn't enough. But as you might suspect from the title of my talk, we're not just going to be looking at rational homology. So our next hope here is, well, this idea seems good. This idea seems promising. It's much easier to compute homology than it is to sort of compute not genus or compute the Thurston Arm. So maybe if I just loosen what I'm thinking about when I'm thinking about homology and consider homology with twisted coefficients, maybe I'll get further. So I won't go into detail on sort of what homology with twisted coefficients is if you aren't familiar with it already. But as a starting point of how to think about this, we can think of homology with twisted coefficients as, well, it's like homology, but we're taking a little bit more algebraic information about the fundamental group of our sutured manifold into account, or of our 3 manifold in general into account. So with twisted coefficients. So this is homology groups, which I'll write h of m e sub alpha, where this is saying my coefficients, alpha is some representation from pi1 of m to, for this talk, I'll just consider some GLNC. So these are homology groups with the added data of this representation, alpha. And you can similarly define twisted cohomology groups. And some basic fact about this, in case you aren't quite sure what world we're living in anymore if we're looking at twisted coefficients. So basic facts, well, to slightly elide this, I'll say every theorem about usual homology still holds here. And what do I mean by this? So universal coefficient theorem, Poincare duality, long exact sequence for pairs. There are some pretty big asterisks next to some of those, but for the most part, I'm just going to treat those as everything still works here. I can still just compute this in some of the same ways that I would normal homology. And in particular, every theorem here encompasses this one of Friedel and Kim. So I can replace this and say, well, let me just cross out all of my rational numbers and replace them with my twisted coefficients. And this is for some representation. And this theorem is still true. If I'm a homology product, if I'm with these twisted coefficients, if I have some representation, any representation, which realizes this as these as isomorphisms, then my sutured manifold is taut. And again, to sort of cross out my rational numbers and replace them with my twisted information. In this case, we say that M is an alpha homology product, or if we don't want to refer to the specific representation, a twisted homology product. Returning to my example right here, this was not a rational homology product, but we don't need to do that much to use this new theorem to realize that it's taut. In particular, we can pick pretty much almost any one-dimensional representation, and that will realize this as a twisted homology product. So for example, well, I guess I'll write this down explicitly. Pick alpha from pi1 of m to GL1C. And we just need this to satisfy if I denote my generators of pi1 of m as x and y like this. Let me just make sure. Let me switch the arrow on this. I just want the condition where I want the image of x times y. I want this not to be 1. So as soon as I have a representation such that the image of the product of x and y is not 1, then this will be a twisted homology product. So it's sort of a fluke in this case that, that it's not a rational homology product. That's sort of saying, well, it's not, if I just pick the trivial representation, that doesn't work here. But if I just, perturb that ever so slightly, I'll be good.
Is the representation alpha on pi1 of r plus or minus just the restriction of the representation?
Yeah. Yeah. So this shows us that this notion of homology with twisted coefficients and looking at twisted homology products gives us more leverage. We can say something that we couldn't before. How much more powerful is this? And so this is where I write Friedel and Kim's name on the board again. And it turns out that the answer is this goes the distance. So precisely, if M is taut, then they show that there is some representation which realizes M as a twisted homology product. So for which M is an alpha homology product. So this says that if we're taut, we should start looking for a representation to certify that because one exists. The question is, how complicated does this need to be? And this theorem really gives no concrete sense at all on how complicated of a representation you need, what dimension you need, because this uses Egel's virtual fibering. In particular, it uses this to find, roughly to find some cover of M where you know that the homology class representing R plus and R minus is, if not fibered, at least on the boundary of a fibered face of your Thurston ball, which then gives you sort of a simple representation realizing this cover as a twisted homology product, which you can then induce down to a good representation for M itself. And when you induce that down, that's blowing up the dimension of your representation. And so the dimension you need is intimately tied to the degree of your virtually fibered of your fibered cover, and we don't know anything about that. So this gives no concrete bound on what N needs to be. So this is approximately the starting point of my program here. I would like to be able to say something concrete about what dimension you actually need. And maybe as a couple of notes, I'll say, so Nathan and Egel have this paper from several years ago where they conjecture, based on a lot of experimental data, that this should be, that a two-dimensional representation should always work. So but there's not really, they show that this is true for some class of manifolds, but this sort of isn't necessarily giving a toehold into how to actually prove this in general. And so I started approaching this as saying, well, let me just try and find some relationship between the topology of my sutured manifold and the dimension of representation I need. So for example, in this case, we saw that, so in my example here, we saw that one-dimensional representation was enough. And you might ask, how often is a one-dimensional representation enough? And well, as of this morning, this theorem got a little bit better. So for any g greater than or equal to 2, there's an example of a taut sutured manifold, taut sutured handle body, which requires a two-dimensional representation. Which is not a twisted homology product for any one-dimensional representation. And in these examples, a two-dimensional representation does always work. But this is just saying, when we're not in our very simple case of being genus 2 handle body with a single suture, we suddenly do need 2 dimensions at least. And so while I haven't been able to come up with any counterexamples to Agel and Dunfield's conjecture precisely, I have been able to show that if we look at a special class of representations, we find bad behavior. So precisely, let's consider solvable representations, which is to say representations of our 3 manifolds with solvable image. In this setting, I can say that for any k, so maybe I should say, so if we have a solvable representation, so a representation of solvable image, we have a notion of complexity of this, namely the degree of solvability. So if your representation is solvable, the derived series terminates at some finite length, and where it terminates is the degree of solvability of the representation. So for any k, I produce examples of taut sutured handle bodies sutured handle body, which is not a twisted product. Which is not an alpha homology product for any solvable representation of degree less than k. And in particular, when I'm considering specifically representations to GLNC, I know what the solvable subgroups of GLNC looks like, and this tells me that if I need arbitrarily high degrees of solvable representations for these examples, then that also blows up the dimension of my representation. I know there's a bound on the degree of a solvable subgroup of GLNC. So to write that down, so in the setting of solvable representations, this conjecture is false, and this conjecture fails in a strong sense, where we need the dimension of representation to be arbitrarily high. However, I guess I will also remark that in these examples, the genus of the handle body is also blowing up. So the genus is roughly something like 2 to the k. So the topology is also getting much more complicated. So this is giving an indication that there is some complicated relationship here. And moving forward, I would like to be able to say something, perhaps strengthen this theorem, find a way of using these ideas to find a broader class of representations for which this conjecture fails, or maybe just find some other way of relating the topology of the sutured manifold to the complexity of a representation, be it in terms of in a solvable one, the degree of solvability, or perhaps looking at, I think a lot of the idea of looking at two-dimensional representations was utilizing some sort of hyperbolic structure to produce a representation. All right, so I will stop there. Thank you.
So do you know if there are two-dimensional representations for your examples that suffice?
I haven't produced them specifically because my construction's a little bit complicated, but I believe they should exist. I think if I spent some more time not applying for jobs and writing down things, then I could come up with the representations, but give me a few months on that.
So you did say that for your first theorem over here, you do have such representations, correct?
Yes, for the first theorem.
That I think is,
there are
she shows that there's
Yeah.
I see.
Yeah.
Oh, I see.
Yeah, the second construction where my examples have, huge genus, that's a little bit harder to analyze in that regard.
Other questions? Let's thank Margaret again. And we'll meet for lunch in the mailroom in maybe 5 minutes.
and there will also be dinner tonight. If anyone is interested in joining us, just let me know. Probably